the glide path of 090 the heading. Approaching into the runway, on course and on the glide path 090 the heading. Final cockpit check complete. You're now over GC8, heads down, on course and on the glide path. Take over, complete your full stop landing. You're clear to Temple Hawk Tower. Good day.
You've just seen several examples of an electromagnetic disturbance traveling through space, from a source to a receiver. In this film, we propose to show you that all these disturbances are electromagnetic waves. We frequently indicate these waves pictorially. Notice the range of wavelengths. Radio waves, about a meter. Microwaves, 1/100 of a meter. Infrared, about 10 to the minus 5 meters. Visible light, 5 times 10 to the minus 7 meters. Ultraviolet, about 5 times 10 to the minus 8 meters. X-rays, 10 to the minus 10 meters. You have just seen the enormous range in frequency or wavelength over what we call the electromagnetic spectrum. You might think that because of this wide variation, that these are different effects. Nevertheless, we believe that they are all basically the same. What do we mean by this? Simply this. If we pick any frequency from the spectrum, we will find the same physical properties demonstrated there as we would at any other part of the spectrum. We're going to investigate the electromagnetic spectrum by doing some experiments showing these common properties. Now, what are these properties? First, the transmission from sender to receiver goes as a wave. This means we expect to find familiar wave properties. Secondly, the waves always arise from accelerated charges. Third, these waves always travel in free space with the same velocity, the speed of light. Fourth, the waves are transverse. By this I mean that the electric vibration is at right angles to the direction in which the wave travels. And finally, that these waves can be polarized. And this property is related to the fact that they are transverse. We mean when we say that they can be polarized, that we can select any plane containing the direction in which the waves travel and can force the electric vibration to lie in that chosen plane. Now, some of these properties can be determined fairly directly. For example, we can easily measure the speed with which the waves travel. We've done this for you already with visible light. Other properties, such as the wave nature, the fact that these waves arise from accelerated charges, and that they are transverse and can be polarized, must be inferred a little more indirectly by doing experiments whose results depend upon these properties. We're going to investigate the wave nature by doing some similar interference experiments in the radio wave region, the microwave region, with visible light, and in the X-ray region of the electromagnetic spectrum. We've chosen an interference experiment because you are already familiar with this as a wave phenomenon. Along the way, we'll show you that the waves are transverse, that they can be polarized, and that they arise from accelerated charges. We'll start first with visible light. You're already familiar with this as a wave phenomenon. But before I do the interference experiment, let me show you that visible light arises from accelerated charges. This room houses the MIT synchrotron. Usually, when we observe visible light, we do not see the details of how light is produced. This is because the light is ordinarily emitted by charges whose motions are on an atomic scale and too small to see. However, there is one example in which visible light is emitted by charges moving on a large scale, where we do understand the detailed motion of the charges. This occurs in the high-energy electron accelerators used in nuclear physics. Behind all this hardware is a large, circular, highly evacuated tube, which looks like a donut, and in which electrons travel in circular orbits with very high speeds. Large magnets are used to deflect the electron paths into circular orbits within the donut. If you could look inside the synchrotron, the donut would look something like this. You recall from work on circular motion that a change in the direction of motion implies a radial acceleration, a centripetal acceleration. Now, if accelerated charges radiate electromagnetic waves, we expect that the centripetal acceleration of electrons in the synchrotron will result in the emission of electromagnetic radiation, in this case, light. There is a porthole in the donut which allows us to look at the radiated light. You are now looking through the actual porthole at the radiated light. The light flickers because the electrons are injected into the machine in short bursts. The important point, however, is that the light arises from the electrons undergoing a high acceleration as they move in their large-scale orbits. Accelerated charges are emitting electromagnetic waves. Here's the apparatus we'll use for the visible light interference experiment. This is a carbon arc source of visible light. The light travels through these condensing lenses and onto a slit here. This slit becomes a single source of electromagnetic waves which travel across here to a double slit, reaching each of the slits in the same time. Each of these slits now becomes a new source of electromagnetic waves with crests leaving the slits simultaneously. These waves radiate out into space in a roughly spherical manner and eventually begin to overlap. Where the overlap occurs, we see an interference pattern. We get a light region where a crest from one slit meets a crest from the other. In other words, where we have constructive interference. And we get a dark region where a crest from one slit meets a trough from the other, or where we have destructive interference. We can show that both slits are involved by closing one of them up and seeing what happens. The pattern of light and dark bands disappears, leaving us with only the diffraction pattern of a single slit. So it must be that both slits are simultaneously sending out interfering waves. Before I can show you that we can polarize visible light, we must first understand what this means. Let me get rid of some of this equipment. When we say we can polarize visible light, we mean that we can force the electric vibrations of all the waves to lie in any chosen plane containing their direction of motion. Now, if light is transverse, that is, if the electric vibration is at right angles to the direction of motion, then what we need to accomplish this is to have a preferred axis in a plane across the direction of the light beam, such that this preferred axis selects those waves whose electric vibrations are parallel to the axis. We have such a device in this Polaroid filter. As you can see, light is getting through the filter. What has happened is that the electric vibrations that get through are lined up with the axis of the Polaroid. I have another identical Polaroid filter, which I'll put in front of this one. And I have previously arranged the two axes so that they are parallel. Light is getting through both of them. Now, if I rotate the second axis by 90 degrees, I should expect to get much less intensity getting through to the screen. This is because the vibrations lined up with the first axis reach the second Polaroid and find there an axis at right angles to them, and therefore they should not get through. Let me rotate it and see what happens. The intensity has gone down. If I rotate it another 90 degrees, the intensity has gone up again. And this is what we expect, because now the vibrations lined up by the first Polaroid again meet a parallel axis and therefore get through. Now, it certainly can't be that most of the light is a longitudinal wave, that is, that the vibration lies along the direction of motion, because if this were so, then the axis of the Polaroid would always be at right angles to the vibration, even when I rotate it. And so no one angle could make any difference, and the intensity should not be affected. So it must be that light is mostly transverse. And if we wanted to make the experiment more elaborate and could use a better Polaroid filter, I could show you that light is entirely transverse. I hope by this simple experiment that you now see that light can be polarized, that it is transverse, and that these two properties are closely related. Let's do an interference experiment in the X-ray region now. This is a typical X-ray tube. It has a very simple structure. This is a glass envelope which is evacuated when in use. There is a cathode at one end which emits electrons when heated. And at the other end, there is a copper plate or anode. A large positive voltage is put between plate and cathode, thus accelerating the electrons to the anode. When they arrive, they have a very high energy and collide with the anode. This violent deceleration causes the emission of electromagnetic waves. We call these waves X-rays. This is the apparatus we'll use for our X-ray interference experiment. There's an X-ray tube similar to the one you just saw in this metal can. The X-rays leave the tube here and strike a lithium fluoride crystal. The crystal looks like this and consists simply of lithium and fluorine ions in a regular cubic array. If you looked at the crystal end on, it would look something like this. The important idea to get from looking at this model is that the ions can be considered as lying in planes. And in our experiment, we are going to consider the reflection of electromagnetic waves from these planes of ions. By using the ripple tank, we can show how this reflection works. Each peg represents a row of ions in the crystal. Water waves will be generated moving towards the model. The incoming wave will successively reach each of the planes. Now, the angle at which the wave enters the crystal is important. If the incoming wave makes an angle with the plane such that the re-radiated waves add up, crest on crest, then we get a strong reflected wave or constructive interference. And that's just what we have now. Notice that there is a distinct reflected wave leaving the model at the lower right of the screen. The condition for constructive interference involves the angle between the incoming wave and the crystal planes. only at the correct angle will we get constructive interference. We are at this angle now, so let's mark the angle as a reference. If we change the angle, like this, the individual reflections mutually cancel, and we get a very weak reflected wave. When I again reach the correct angle, I get constructive interference, a strong reflected wave. In our X-ray experiment, we will be able to detect constructive interference with the lithium fluoride crystal. We can see the entire experiment on this diagram. The electron beam in the X-ray tube hits the anode, and X-rays are emitted. They strike the crystal at an angle theta, leave at the same angle, and enter a Geiger counter detector. The output of the Geiger counter is put on an electronic counter. What we will do in this experiment is to vary the angle theta and look for those special angles where we get constructive interference of the reflected waves. Now let's do the experiment. As I turn this dial, I'm varying the angle theta between the incoming waves in the crystal and between the outgoing waves and the crystal. Notice both the lights on the electronic counter and the clicks. We get a click every 64 counts. The intensity is increasing, and I'll stop at a peak. This corresponds to constructive interference between the reflected waves. As I move off the peak, the intensity drops down. And I'll continue to vary the angle. Now we're coming to a second peak, and I'll stop at its maximum. Notice that we're getting interference phenomena, which, as you know, are characteristic of wave motion. We're going to do a microwave experiment now, which will be directly analogous to the Young's optical interference experiment you saw just a little while ago. Only in this case, the waves will have a frequency of 9,000 million cycles per second, corresponding to a wavelength of about 3.3 centimeters. We'll produce the microwaves in a tube called a klystron. Here's one. The microwaves come out from this antenna. We pump electric charge or current up and down this antenna, and the accelerated charge sends out the waves. We've got the same klystron in this metal can. The accelerated charges on the antenna start an electromagnetic wave down this pipe. The wave reaches this point and splits and arrives at these 2 points with identical phase. We then feed them through these 2 horns out into space. The purpose of the horns is to minimize reflections, which are caused when we make the transition between the pipe and the space. The 2 horns in this experiment will act just like the double slit did in the optics experiment. Here we have a detector which is sensitive to the resultant electric field tangent to it. We're going to move the detector back and forth through space this way, thus sampling the total electric field resulting from both these horns at each point in space. The output of the detector will be fed to this meter. Now let's do the experiment. As I move the detector this way, across the incoming waves, you can see that the deflection on the meter goes through a series of maxima and minima. You can also hear it on a loudspeaker we've hooked up because we're chopping the microwaves 1,000 times a second. Just as in the optics experiment, when a crest from one horn meets a crest from the other, we get a constructive interference or a maximum at the detector. And when a crest from one horn meets a trough from the other, we get destructive interference or a minimum on the meter. In order to show that this is really an interference phenomenon, we have to show that both horns are simultaneously involved in producing the resultant field at the detector. Now you'll remember we stopped at a minimum. Let's close one of the horns and see what happens. The intensity on the meter went up. This means that the field from this horn can no longer cancel the field from the other. Let's go back to a maximum. And I'll again close one of the horns. In this case, the intensity on the meter went down. This was because we closed one of the horns, thus leaving only the intensity due to the other one. It's easy to show that microwaves can be polarized. If we place a screen like this between the horn and the detector, you can see that in this position the intensity on the meter is relatively unaffected. But if I rotate the screen by 90 degrees, the intensity on the meter drops almost to zero. The reason for this is that in the second position, the electric field was parallel to the wires. This set up strong currents in the wires, which converted much of the microwaves to heat. In the first case, the electric field was perpendicular to the wires, not much current flowed, and most of the microwaves got through. You have noticed that in this experiment, the microwaves were already polarized as they left the horns. The important thing is that we could polarize them, just as we were able to do with light in the optics experiment. And once they were polarized, they retained this property as they traveled through space. We showed you this when we placed the screen at some distance in front of the horn. This meant that the microwaves had to carry their polarization property with them as they traveled to the screen. Incidentally, it's easy to measure the wavelength of microwaves. If we place a reflecting screen behind the detector, we can pick up a standing wave pattern. And by measuring the distance between minima, we can get the wavelength of microwaves. Let's go do it. I'll put up a reflecting plate in back of the antenna. The wave coming out of the horn comes down this way and bounces off this plate. At the position of the antenna, we have both an incoming wave and a reflected wave. As you know, the sum of two such waves gives a standing wave. I'm going to move the antenna in this direction and follow its position with this pointer. In order to allow me to measure the standing waves, I'll put this centimeter stick behind it as a scale. As I move the antenna, we go through a minimum, maximum, and let me stop at a minimum and mark the scale. Now I'll move the antenna to the next minimum. And mark the scale again. The difference between these two marks is just 1.65 centimeters. As you know, standing wave minima occur every half wavelength. This means that the wavelength of these microwaves is twice 1.65, or 3.3 centimeters. The most common use of microwaves, radar, is probably familiar to most of you. In radar, we shine microwaves onto an object and measure the time it takes for the microwaves to go to it and come back. If we take half this time interval and multiply it by the speed with which microwaves travel, we can calculate the distance of the object. This speed turns out to be exactly equal to the speed of light. Our last experiment is in the radio wave part of the spectrum. Here we will work at a frequency of 140 million cycles per second, corresponding to a wavelength of about 2.1 meters. Because of this large wavelength, we obviously have to work with much larger physical apparatus and in a larger area. This large field will be perfect for our experiment. Aside from the larger equipment which we'll use and the lower frequency, this experiment will be identical to the one you saw with microwaves. There are two antennas set up about 20 feet apart, which in this experiment will take the place of the two horns in the microwave experiment. The antennas are fed from the same transmitter, thus making them coherent sources of electromagnetic waves. We're going to pick up the resultant electric field from the two antennas with a similar one here. The way the waves come out from these two sources is just the way the klystron antenna sent out microwaves. What we're doing is to pump electric charge from the transmitter into and out of the antennas and back and forth at the rate of 140 million times per second. It is this accelerated charge which sends our electromagnetic waves off. Now, if our ideas of the interference of electromagnetic waves are correct, we'd expect to find regions of constructive and destructive interference in the space here in front of the two sources. So what we're going to do is to move our pickup antenna back and forth in space, thus sampling the resultant electric field from the two sources. We'll convert the received signal into sound on this loudspeaker and also into a deflection on the meter. The reason you can hear the sound is because we're chopping the transmitter signal 1,000 times per second. Now let's try the experiment. As we roll along, moving the detector, once again, we go through a series of minima, maxima, and minima. Now let's try it again. And I'll stop at a minimum. To see that this is really an interference effect, let's disconnect one of the antennas. John, you see the intensity has gone up, both on the meter and in the sound level. This is because we've disconnected one antenna, and so it can no longer cancel the field due to the other. Let's reconnect it. Our intensity is down again. We're at a minimum or a point of destructive interference. Let's try the same thing at a maximum. And let's disconnect one of the antennas. Now you see the signal has dropped. This is because we've removed an antenna, so we're receiving the field due to only one. And so we get a smaller signal. So you see, once again we have wave interference, this time in the radio wave region of the electromagnetic spectrum. There's one more wave property I want to show you, and that is that radio waves are polarized. The waves being transmitted by our antennas are polarized such that the electric disturbance is parallel to the metal rod or antenna. This is because we're pumping charge or accelerating it back and forth along the rod, and it is this accelerated charge which starts the wave going parallel to the rod. We can show the polarization of these waves as actually received by rotating the antenna, John, would you rotate it by 90 degrees? You see, as he rotates it, the intensity drops, and at 90 degrees, it has gone down to 0. This is because the antenna is now sending a radio wave polarized such that the electric field is perpendicular to the antenna that is receiving it. Because they are perpendicular, you get a minimum received signal. Let's rotate it by another 90 degrees and see what happens. You see, the intensity has gone up again. This is because the two antennas are again parallel. The wave being transmitted is polarized such that it arrives at the receiving antenna with its electric disturbance parallel to the antenna and is now fully received. Let's see what we have accomplished. By doing a simple interference experiment in 4 widely separated regions of the electromagnetic spectrum, I've been able to show you that the interference effects arise from waves, that the waves are transverse and can be polarized, that they arise from accelerated charges and travel with the speed of light. It is due to these common properties that we believe in the unity of the electromagnetic spectrum.